The interview with Stephen French is beginning now. And the first thing I'd like to ask you about is that the first thing you did on identity and individuality in quantum physics and so on. Could you say a little bit about the identity of indiscernibles with sort of the arguments there? Could you say a bit about that?
Right. So the project that I was working on in the PhD, as you know, had to do with identity and individuality of quantum particles. And the standard view that really went back to the likes of Born and Heisenberg in 1926-27 was that the way quantum statistics treated particles meant that you had to consider them to be, in some sense, not entirely clear, some sense, non-individuals. And, well, you remember you and I worked on the idea that, in fact, they could be considered to be individuals. And the most obvious way in which one can articulate the grounds, if you like, of that individuality is in terms of the identity of indiscernibles. Leibniz's famous principle, which basically says that putting it very crudely, no two things are exactly alike. No two things share all of their properties. And of course, a lot depends on what you're including in the scope of their properties. Leibniz, of course, was thinking in terms of his monads. But it becomes an interesting question whether that principle applies to physical objects. One can, recall the image of the princess scurrying around in the gardens looking for two leaves that are exactly alike. And then the question comes down to whether quantum particles are considered to be completely indiscernible or not. And in that paper of ours from the British Journal of Philosophy of Science, which I think is 1989, long time ago now, we argued that the principle of insofar as the principle can be said to apply to quantum particles, it was violated by both fermions and bosons. Now that depends on establishing a certain view of what we're going to take the properties of the particles to be. Particles in an entangled state can't be assigned properties you can't assign properties to the distinct particles, and so we chose the approach of using D'Espagnat's idea of improper mixtures, and on that basis you can establish in that context that both fermions and bosons can be said to have fermions and bosons in entangled states can be said to have the same properties as one another, and therefore that they are completely indiscernible, and so the principle is violated. Interestingly, Simon Saunders has revived that debate, which was sort of went quiet, I think, after our paper was published, by adopting a Quinian perspective on what we should take the properties to be, and has, together with Fred Muller, has developed this idea of weak discernibility, that certainly fermions can be said to be weakly discernible by virtue of standing in an irreflexive relation to one another. I think it's still a sort of interesting question whether bosons can be said to stand in such a relation, and I know Muller and Sieving think they can, but I think there's some problems with that. But it's a very interesting project, and it revives a kind of Quinian form of the identity of indiscernibles. And there's a lot of debate at the moment as to whether weak discernibility is sufficient to ground the individuality of the particles, whether in fact we should consider quantum particles to belong to a different category. I think Muller calls them relationals. Reminds me of, I think, your category, Michael, ephemerals. So there's a lot of interesting discussion, I think, going on, following Saunders' revival of, as I say, this sort of
Now,
wily inclusion of identity indiscernible.
there's something that came up there about the question of the role of paraparticles. Could you say something what these paraparticles were? Or are?
Paraparticles are very interesting. So again, the standard view is that there are only two kinds of particle statistics in the world: Fermi-Dirac and Bose-Einstein. And putting it fairly crudely, Fermi-Dirac statistics are obeyed by electrons and sort of material particles, and Bose-Einstein statistics are obeyed by photons and so forth, the force carriers. And many people thought and continue to think those are the only two. But in fact, you can show group theoretically, if you represent those alternatives in group theoretic terms, you can show that there are lots of other kinds of statistics. Dirac knew this even though he wasn't a big fan of group theoretic methods, back in the 30s he knew this. And this was in effect rediscovered in the late 50s and early 60s. And specific forms of these non-standard statistics were worked out, first in quantum field theory, and then within sort of standard quantum mechanics. Greenberg and Messier had a famous paper on this, and Greenberg famously applied one of these non-standard forms that became known as paraparticle statistics to quarks. There was a problem in accounting for the statistics of these new entities that were being proposed, quarks, and he proposed paraparticles in order to account for their collective behavior. And then Hanna Nambu basically showed you could achieve the same result by introducing a new parameter that subsequently came to be known as color. And so quantum chromodynamics was born, and the paraparticle sort of alternative fell by the wayside. I mean, once you could gauge quantum chromodynamics, really interest in paraparticle theory really dropped away in the 70s and early 80s. But it's an interesting theoretical idea that there are lots more possibilities out there, as it were, in possibility space. They just don't happen to be realized, to be manifested in this world.
Could I ask you now to say something about Heinz Post, and his famous seminar, and the way he used to reduce the first year students to some sort of a terror, suspense. What's your recollection of that?
Post was one of these incredible charismatic figures, I think. When I started the PhD program, there was only one other person on the program, Jimmy Anderson, who introduced me to my wife, and the two of us would take Post's class in the philosophy of science. And it consisted of a close reading of Popper's Logic of Scientific Discovery, very close reading. And it took place, I think it was on a Wednesday or Thursday afternoon. And Post, I think he had some eye problems.
Right.
I think Post had...
I'll let it go there.
Post had some eye problems and refused to turn the lights on. And so obviously as we went through the autumn months into November, the room would get darker and darker until by 4 o'clock, 4:30, the room was completely pitch black. And there would just be this disembodied voice discoursing about Popper on probability, and there was no possibility of taking notes. We just sat there and listened and tried to interject. It was, I think, for someone who came from physics as I did, with no experience really of philosophy, it was a bizarre but also somehow magical experience. And the seminars were incredible. They took place in old Jathinga, so that generally the postgrads pack up in the peanut gallery, and they were huge fun for us and an incredible learning experience. Also a bit of a bear pit, because almost every seminar post would solemnly announce that the speaker had requested a clear read-through, that all questions must be held back until the very end. And of course, within 10 minutes, the first question would be asked, and it would be invariably from Post himself, and that was it. It then became a free-for-all with everybody, John Dorling and others, leaping in, and the speaker just had to fend for his or herself. As I say, it was a great experience for postgrads, because I think we felt that you really got to the heart of a topic of a presentation, instead of just having to sit there and listen to someone read out a paper. You were involved in this discussion, but at times it did get quite, I think, brutal. And one of the traditions at Chelsea College is that at a certain point in the writing of your thesis, a postgrad had to give one of these seminars, and I think that was by far the most terrifying experience in my academic career, having to stand there in that bear pit.
Now, could I talk a bit about this business of structural realism? And there's a big debate between Chow and also interviewed on it, and he doesn't take very kindly to the ontic realism. But could you just explain what's going on there? Just tell me about this.
This, for me, follows from the work on the path of individuality. It seemed to me at the end of my thesis that there were two quite plausible options with regard to the individuality of quantum particles. One, you could regard them as non-individuals, and together with a Brazilian logician, Décio Krauss, tried to articulate a sort of formal apparatus, quasi-set theory for accommodating that non-individuality. Or you could regard them as individuals, and you could articulate that in terms of weak discernibility or whatever. Well, then you have a kind of metaphysical underdetermination. And I think Van Fraassen posed a challenge at the end of his book on quantum mechanics. And the challenge goes like this. If you're going to be a realist about electrons, you need to say something about what they are. And if you say they're objects, they're out there in the world, it seems the obvious thing to say. You then need to say, well, are these individual objects or not? And physics can't tell you. There's an underdetermination there. And I think the realist needs to respond to that. And one way of responding is to kind of retreat from this metaphysics of objects and say, look, there are electrons, they're out in the world, but what they are, they're not objects. Well, what are they then? What's the alternative? Well, one alternative, and it's a move that goes back to people like Eddington and Cassira, who's often neglected in these discussions, is to say that they are nodes in, or aspects of, or features of the fundamental structure of the world. And that's the core idea of ontic structural realism. It's an idea that was really, I think, fully and sort of clearly articulated in this debate by James Ladyman in a paper in 1998, and he was my first PhD student at Leeds, and he wrote this book with Don Ross, Everything Must Go, defending that view and articulating some of its implications. And in my own work, I wanted to emphasize the role of symmetry, and in particular the group theoretic representation of that symmetry in the articulation of what we mean by structure. And so the view amounts to the claim that all there is in the world is structure. And then the challenge for the structural realist is to say what that structure is. And one way of doing that is through the resources that physics and mathematics give us, through the laws and the symmetries and so on, as represented group theoretically. So that's the core claim of ontic structural realism. It claims that not simply that all that we know is structure, but that all that there is structure.
Well, then later on, the chair of philosophy at Bristol came up, but you decided not to go for it. Can you make a comment on that?
Well, it was one of the most difficult decisions I've ever made. Things obviously went very well at Bristol. I was very attracted to the post of Bristol. James was there, and I knew that if I went to Bristol, he and I would continue a wonderful collaboration. But there were personal reasons having to do with our son, who was about to go into secondary school. We had concerns about finding schools in Bristol. We had concerns about finding a house down there, given that house prices are so different. And I mean, academically, I think the Bristol department is an incredible department. It's gone from strength to strength. But also there's lots to say, obviously, about Leeds. Leeds has this sort of unique combination of historians of science and metaphysicians and sort of regular philosophers. So I can sort of hobnob with both sides, as it were, and it's been very productive. But I have to admit, there are times when I think, what would have happened if I had gone down to Bristol.
Well, could I finally ask you a question about what philosophers have influenced you yourself, particularly in your own work? Could you say something on that?
Not wishing just to flatter you, Michael. You yourself, of course, the way you approach philosophy of physics. Van Fraassen, I think, has had a tremendous influence on me. Both the span of subjects that he's covered, from philosophy of physics to representation, but then also Newton da Costa, a great Brazilian logician and philosopher, for his way of approaching problems with the kind of formal gusto that he brings to them. More classically, people, certainly in the 20th century, people like Carnap and Cassira. As I said before, I think Cassira is, or has been, neglected. His work has been revived by the likes of Friedman and others, but I think he's still, and Tom Reitman, he's still quite neglected. Reading his work just showed me, again, what one could do in philosophy, the breadth of what one could do, and the insight that one could gain by looking at all these different fields and trying to bring them together under this kind of synergetic vision. So I think those would be the biggest influences. Obviously, through Cassira, to some extent, Kant. Michela Massimi, my colleague and co-editor on the British Journal of Philosophy of Science, would be laughing if she heard me talking about the influence of Kant on me, I would think. And then, Leibniz, going back even further, I think reading some of Leibniz's sort of crazier work on the monadology, for example. It is crazy in many respects, but it's also quite profound and eye-opening.
Well, anyway, thank you very much indeed. And what I'm going to do now in a moment, I'm going to switch off and the interview with Stephen French is coming to an end.